Right. On to the next one. Now he says that A be the set containing 1, 2, 3, so on till 100. Now he says if number of subsets of A containing 4 elements, that means we only need to talk about subsets which contain 4 elements. So maybe I can have set containing 51, 63, 74 and 98. Cool. Now he says we need 4 element subsets such that the sum of all elements is divisible by 3. Okay. And he says this is alpha, then you need to write the sum of all digits of this number. Basically, I need to find alpha. Right. Now, I need to count number of subsets. In fact, I need to count number of 4 element subsets such that sum of all elements is divisible by 3. Now, divisibility by 3, that is coming into the picture. That means I can use the forms of the number. I know any number can either be of the form 3k or 3k plus 1 or 3k plus 2. Right? In these numbers, obviously, some would be of the form 3k, then 3k plus 1, then 3k plus 2. Let me count how many 3k numbers are there of the form 3k. So first number is 3, then we have 6, then so on we will have 99. Right? This is the number 3k form. Now, if I need to count it, I can say 3 into 1, 3 into 2, and then this is 3 into 33. So 1, 2, so on till 33, I have 33 numbers. Right? Then 3k plus 1 type. Right? It will obviously start with 1, then I will have 4, and then I will have 97. I need to count this. Right? In order to count this, what I can do is I can do this. 0, 3, so on till 96. Right? Because since gap is 3, what I'll do is I'll reduce the number. Now, the number of numbers over here would be equal to the number of numbers over here, because corresponding to each I'm writing it here. Or you can use the AP method, whatever you want to do it. So this is 3 into 0 plus 1. Or you know what, just leave it. This is 3 into 1. Then I have 3 into 2. And then I have 3 into 32. And additional one number, so again it is 33. Actually, we are forgetting one number. 97 ke baad 100 bhi aayega. Yeah. So this has to be 34 in number actually. Careful. Right. Similarly, you can form you can find how many 3k plus 2 numbers are there. That is obviously I'll start with 2 and then I will end at 98. These will turn out to be 33 in number. Right? Cool. Now the thing is I need to have 4 element subsets. 4 elements such that the sum of all these numbers have to be divisible by 3. Now, first case is obviously all of them can be of the form 3k. 3k, 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 3k. Obviously, since each number is of the form 3k, the sum of all of these would be of the form 3k. Right, done? So, 3k, 3k, 3k. Now, the thing is, I'll keep these 3 as constant. Do you think I can change this? 3k plus 1? The answer is no. Right? Because then the sum is not divisible by 3. Do you think keeping this as constant, I can keep this as 3k plus 2? The answer is no. Because again, the sum is not divisible by 3. So that means I have exhausted all the cases when I have these 3 3k. That means this I have exhausted, now I need to change this one. So instead of 3k, I can have 3k plus 1. Right? Obviously, I will not put 3k over here, right? Because that does not make sense. I can put 3k plus 2. Right? Another case. So I have exhausted all those possibilities where 3k is there and here 3k plus 1 is there. Now, you can say, ma'am, you can put 3k plus 2 over here. And then corresponding to this, you can have 3k plus 1. Mind it, there is no difference between this and this. Why? You can take numbers like 3, 33, and you can take 34 and 35. Or you can take numbers like 3, 33, 35, and 34. Do you think this set is different from this one? Absolutely not. So mind it, these 2 cases are same. So I will not be writing it. So this is done. Right? So that means I have exhausted all the cases when I have 3k over here, right? So let me have 3k plus 1 over. Right? Now, next one, obviously I will not put 3k, I can put 3k plus 1. Then I have to put 3k plus 1. Another case. Now, do you think instead of 3k plus 1, I can have 3k plus 2 over here? No. Right? So I have exhausted this case now. So 3k as it is, 3k plus 1 as it is, I will change this now. So let this be 3k plus 2. Now, the thing is, if that is the case here, 3k have to be there. But this case already counted, so I will not count it again. Right? So I've exhausted all the cases when 3k plus 1 is coming over here. So let me put 3k plus 2 over here. I will not put 3k plus 1 because already exhausted here, and I can put 3k plus 2. Right? Again, not 3k plus 1 because it does not make sense. Then 3k plus 2. Another case. Right? Now, I have exhausted all the cases when 3k is there. Now, let me change this only. So, let this be 3k plus 1. Right? Next have to be 3k plus 1. Now, the thing is, you can say put 3k plus 1 again. The thing is, then I have to put 3k over here. Right? Already counted. Then, you can say put 3k plus 2 over here. Then, you need to put 3k plus 2 over here. This is the case that I can do. Right? Now, I have exhausted all of these cases. Now, you can say put 3k plus 1 as constant. You will change this. But mind it, now I have established all of these. The rest of this would be repetitions of all of these 5 cases. So, that means in total, I have 5 different cases. In each of these, if I can find out the number of subsets, I can find the total number of subsets. Right? Which is an easy job. Let's see. Now, he says first case, when all the 4 numbers are of the form 3k. That means out of these 33, I need to choose 4. That is done in 33, 3, 4 ways. Done. Second. Now, second case, 2 is of the form 3k. 1 is 3k plus 1, 1 is 3k plus 2. Right. First, let me choose 3k. Out of these 33, I need to choose 2. So, 33, C. Corresponding to this, I need to choose 3k plus 1 also. So, out of these 34, I need to choose 1. So, that is 34 C1 into last 3k plus 2. Out of these 33, I need to choose just 1. So, corresponding to that. So, that is 33. Let me rewrite this again. This was 33 C2 into 34 C1 into 33 C1. Done? Right. 1 3k number. So, that means I have 33 C1. Now, 3k plus 1 numbers. That means out of these 34, 3 I want. That is 3k, 34 C3. Here, 33 C1 into 33 C3. Then here, I have 34 C2 into 33 C2. Right? In each of the cases, I found out the number of subsets. If I add all of these, I'll get the total number. Right? Mind it, I do not want alpha. I want alpha divided by 33 into 8. This actually turns out to be 4951. Right? In fact, I want the sum of digits of this number. So, if you add the digits, obviously, the answer will turn out to be 90. Alright, next one. Now, he says, write the sum of digits in the largest positive integer n. Largest positive integer n. For which n cube plus 100 is divisible by n plus 10. Right? Now, I know that this polynomial is not exactly divisible by this. But for some values of n, this value would be divisible by this value. In fact, I need to find out the largest possible value of n. Right? So, n cube plus 100 should be exactly divisible by n plus 10. So, let me just divide it first. Right? When I do that, obviously, you can do the division on your own. I will actually get n plus 10 into n square minus 10n plus 100. Right? And this will plus minus 9. Right? Now, he says this number should be exactly divisible by this. That means I am talking about that integer that comes. This integer should be exactly divisible by this. So, let me shift this to that side. Right? So, take n plus 10 common from the right side. So, this becomes n plus 10 as it is. This n square minus 10n plus 100 minus 900 divided by n plus 10. Right? And obviously shift this to this side. So, n cube plus 100 whole divided by n plus 10. Right? Now, mind it, this has to be an integer. Now, clearly n we are putting in positive integer value. So, that means this is an integral value. I just have to make sure that this is an integer. 900 divided by n plus 10 should be an integer. Right? In fact, I want the greatest possible value of n. N should be greatest. That means n plus 10 should be greatest. Now, 900. Here, maybe I can have 1. I can have 2. I can have 3. I can have 4. Because all of these, I am listing out the factors of 900. But now I want this number to be the largest, right? That means I can look for the factor of 900, which is the largest, which will be 900 itself. Obviously, the highest factor of 900 would be 900. If I want this to be the highest one, largest one, 9 plus 10 has to be 900. Right? And obviously, this will turn out to be 890. Right? Now he says, write the sum of digits in the largest positive integer. So, sum of digits, that will turn out to be 70. Right. On to the next one. Now he says, consider a set S that contains m greater than or equal to 4 elements. Right. So that means number of elements should be greater than 4. It can be 4, greater than or equal to 4. It can be 4, it can be 5, it can be 6, and so on. So we're talking about such a set. And obviously each of these numbers is a positive integer. Right. And since it is a set, obviously the numbers cannot be equal to one another. The numbers have to be distinct. So that means 4 elements, all 4 numbers have to be distinct. 5 elements, 5 numbers have to be distinct. Right? Now he says we call S boring if it contains 4 distinct integers A, B, C, D such that A plus B is equal to C plus D. That means we'll call a set boring if I can find out 4 integers out of it such that sum of 2 is equal to sum of other 2. Right? He has given us as an example also 2, 4, 6, 8, 10 is a boring set. Why? Because 2 plus 8 is equal to 4 plus 6. We have found out 4 numbers here over here such that sum of 2 is equal to sum of other 2. That is why this set is boring. Right? Now he says we call S exciting if it is not boring. That means if you are unable to find 4 integers such that sum of 2 is equal to sum of other 2. So in exciting, those two sums will not be equal. So this one, obviously you take any number, sum of any 4 numbers, sum of 2 will not be equal to the sum of other 2. Done. Now on to the actual question. He says write number of 5 element subset. 5 element subset. So maybe I can have 2, 3, 5, 6, 7. Right? But we need to have only those subsets which are exciting. That means sum of 2 integers should not be equal to sum of other 2 integers. I have to make sure of that. Now, sum should not be equal. How should I start the question? Now, sum should not be equal. Condition is there on the sum. So maybe I can find out the possible sums first. Right? Maybe the sum of numbers can be 11. Maybe the sum of numbers can be 5. Right? So maybe let's write all the possible sums that are there. So suppose we are talking about the sum 3. Right? Now, possible pairs along with it. Now, 3 obviously can be done in 1 and 2 ways only. So 1, 2, that's my pair. Right? Now, next sum can be 4. Right? 4 can be done in 1, 3, only one way. Okay. 5. Sum 5. That means I can have 1, 4 and 2, 3. 1, 4 and 2, 3. Right? Obviously, I should be putting commas in between, but I will not to save my time. Then, sum 6. So, I'll have 1, 6, 2, 4. 1, 6, 2, 4. Then, sum 7. 1, 6, 2, 5, 3, 4. 1, 6, 2, 5, 3, 4. Now, do you realize it why I'm writing these down? Because I know if I have 1, 5 in my subset, I cannot have 2, 4 together. Maybe I can have 2, maybe I can have 4, but together I cannot have. Right? So that is why I'm writing down all the pairs which will have problem with each other. Right? So 8, 1, 7, 2, 6, 3, 5. 1, 7, 2, 6, 3, 5. And so on. You can write all the pairs. I will not waste my time on that. Obviously, you can do it yourself. So 9, 1 turns out to be 1, 8, 2, 7, 3, 6, and 4, 5. And then I will have 10, 2, 8, 3, 7, 4, 6. Then I have 11. That is 3, 8, 4, 7, 5, 6. Then I have 12. That is 4, 8, 5, 7. Right? Then I have 13, which is 5, 8, and 6, 7. Then I have 14, that is 6, 8. And then last sum that is possible, that is 15, which is 7, 8. I have exhausted all the sum of 2 numbers which are there. Right? Now, I have to find 5 element subsets. In fact, I need to find all of them. So let's start by making the cases. Right? Let's start with maybe I have 1, maybe I have 2. Right? Now I need to put in more numbers. First of all, 5 element subsets should be there. Also, let me write down the numbers also. 1, 2, 3, 4, 5, 6, 7, 8. out of these numbers I'll take. So I'll start with 1, 2. Right? Wait. 1, 2 is there. Do you think I can put in 3? No problem. Right? Now mind it, 1, 3 is there, 1, 2 is there, which are absolutely fine. They don't have a problem with each other. Now 1, 2 done, 1, 3 done, 2, 3. Right? Now 2, 3 cannot occur with 1, 4. That means 1 is already there. I cannot put in 4. So 4 cancels. Right? Okay. Now if I cannot put in 4, let me put in 5. Let's see what happens. Now 1, 2, 1, 3 is absolutely fine. 1, 5. If 1, 5 is there, 2, 4 cannot be there. That is absolutely okay. Then 1, 5 exhausted, 2, 3. Let me check. 2, 3 will have a problem with 1, 4. It's okay. 2, 5 will have a problem with 3, 4, which will not come. 2, 5, yeah. 1, 6. That means 6 cannot come now. Done? Okay. Now 6 cannot come, so maybe I can have 7. Let's see whether that works or not. 1, 2, 1, 3, 1, 5, 1, 7. Up. Now the thing is, if I put in 1, 7, it will clash with 3, 5. So that means I cannot put in 7 also. So let me put in 8. Let's see whether that works. Now 1, 2, 1, 3, 1, 5, 1, 8. Sorted. Nobody is having problem with each other. 2, 3, absolutely fine. 2, 5, absolutely fine. 2, 8, here. No problem is here. Cool. 3, 5, you can check. 3, 8, you can check. 5, 8, you can check. Right? So that means one such exciting subset is this one. 1, 2, 3, 5, 8. Cool. Right? Now, I started with 1, 2, 3. Right? Obviously, I exhausted 4 cannot come, then I put in 5. So let me put in 6 now. Do you think I can have 6 over here? Let's see. Cool. So 1, 2 is fine, 1, 3 is fine, 1, 6. 1, 6 is here. That means 2, 5 obviously done, 3, 4 obviously done. 3, 6. If I put in 3, 6, that means I cannot put 5, 7, 8. 5, so it's okay. I cannot put 7 and 8. That means this one will not work for me. Right? So 6 I cannot have. Obviously I cannot have 7. That is done. So that means 1, 2, 3 have been exhausted. So let's come to 1, 2, 4. Right? 1, 2, 4. 3 I'm not putting in because so let me check the next one. 1, 2 is fine. 1, 4. 1, 4 is here. 3 को डालना ही नहीं था. 2, 4. I cannot put in 5, so I have put in. I can put in 6. Let's see. 1, 2, 1, 4, 1, 6. If that is the case, 5 and 4 are already not there, so it's okay. 2, 4. 2, 4. 5 is not there. It's absolutely fine. 2, 6. I cannot put in 7 now. So that means I can put in 8. But the thing is, along with 4, 6, where is 4, 6? I cannot have 8. So that means I cannot put 7, I cannot put 8. That means this is also done. Right? So 1, 2, 4 is exhausted. You will realize 1, 2, 5 will not work. In fact, 1, 2 thing will not work. Right? You'll move on to the next one. You will exhaust 1, 3. Right? You need to exhaust it because this is a 10 marker. You need to put in some effort. Right? The only other set that you will find that is exciting, that is 1, 4, 6, 7, 8. Right? So he asked, write the number. So there were just 2. 0, 2 is the answer. Now, second part was related to this one. He says, in above question, write the sum of all elements of each possible 5-element subset. So you need to add these and write the answer, and that will turn out to be 45. All right, on to the next one. Now, this is obviously the third part of 23rd question. He says, define remainder a comma b to be the remainder when a is divided by b. Right? So, for example, we have remainder 10, 7. So, when 10 is divided by 7, the remainder is 3. That is why we have written it 3. Remainder, when 20 is divided by 5, obviously remainder is 0. When 3 is divided by 4, the remainder is 3. Now, he says take n greater than or equal to 10. So, either I can take 10 or I can take 11 or I can take 12 and so on. Right? Now, he says for each positive integer k, where 1 less than equal to k less than equal to n, we have defined the terms like this. Right? Now, he says write the number of all integers. So, n varies from 10 to 89. 10 is included? Yes. For which the set this of n integers is exciting. Right? Now, the thing is, the question doesn't start. right condition is there, I do not understand how to start the question. So what I can do is, now he says, define this when n varies from 10 to 89. Let me take some value of n in order to understand, right? So maybe you can start with 10, I'll start with 11. No rule about it. So I will take n to be 11, right? So that means my k varies from 1 to 11. That makes sense, because we will be talking about the terms x1, x2, x3, x4, so on till x11, right? Now, how do I write x1? He says 2 into n was 11, so I'll say 22 into, now 22 is multiplied by this. Remainder, when, now k we have taken to be 1, 1 square is divided by 11 in this case, so that is 1, plus k, which is 1. First term, right? No need to simplify it, don't worry. Second term. Now, obviously 2n remains same, so 22 will be there, into. Now, 2 square, remainder when 2 square as in 4 is divided by 11, that would be 4 plus 2. Next, 22 as it is, into. 3 square divided by 11, that is obviously 9 plus 3. Right? So, let me write the terms, let's see what happens. Right? So, x4 is nothing but 22 into 5 plus 4, fine. Till now, I cannot see anything. Right? x5 is 22 into 3 plus 5. Then 22 into 3 plus 6. Okay. x7, that is 22 into 5 plus 7. Then 22 into 9 plus 8. Then 22 into 4 plus 9. Then 22 into 1 plus 10. Last, obviously, 22 into 0 plus 11. Right? Now, if you look, can you see what is the observation over here? I think observation is pretty clear. 14953, then 359410. This thing, this thing. Okay, note it down. And also 3 is twice. This you must have analyzed. If you don't understand the question, at least we'll take some values and see what is happening. Right? Next, we can take n as 12. Let me write that one also. So that means I'll write x1 first. So x1. Now 2 into 12, that would be 24. Into remainder when 1 square is divided by 12. So I understand that is 1 plus 1. Cool. Next would be 24 into 4 plus 2. Next would be 24 into 9 plus 3. Right? Next would be 24 into 4 plus 4. Then 24 into 1 plus 5. Then 24 into 0 plus 6. Can you see the pattern again? Right? x7. Now it will be 24 into 1 plus 7. Then 24 into 4 plus 8. Then 24 into 9 plus 9. 24 into 4 plus 10. Then 24 into 1 plus 11. Then last 24 into 0 plus 12. Since we have a lot of time for the 10 markers, we need to put in a little bit effort. Pattern will only be observed if you write the term. Right? Now you can see the pattern again. 1, 4, 9. 4, 1. Then obviously 0 will come. 1, 4, 9. 4, 1, 0. Done? Now let's look at this. Now first of all, I need to find those subsets which are exciting. That means sum of 2 should not be equal to the sum of other 2. Right? First of all, I'll check for this one. I'll check for each and every case. Obviously, I will not say, oh, sum of this, sum of this, sum of this. I'll check like this. Sum of this, sum of this, sum of this. Right? It hardly takes time. Why? Because here 22 will be common. So, in adding terms, it is a little bit easier. Right? Now, look for 4 integers over here such that the sum of first 2 is equal to sum of other 2. In this case, you can. If you take these 2, I'm just taking randomly 2. There might be others. Obviously, there will be others. Right? 4 and 8. 4 and 4. This is the 10 one. Right? You can see 24 into 4, 24 into 4 plus 2 plus 10. Same thing. 24 into 4, 24 into 4 plus 4 plus 6. Right? The sum is same. Now here the sum is same. Right? Here the sum is not same. Now you need to analyze a little bit more. You will check for n is equal to 30. right? Again, when you check for n is equal to 13, you will realize you cannot find any, right? Why? Because repetition, see, 3 occurs twice. That happens in 13 also. Repetition is there. Then you will check for n is equal to 14. You realize that repetition is not there, right? And that is why somehow you are able to find the numbers, 4 numbers, so that sum of 2 is equal to sum of other 2. That happens in 14. 15 also, you will not be able to find this kind of repetition. That is why you are able to find it. 16, the same way. Now, when you come to n is equal to 17, again repetition is there. 3 comes here, right? In n is equal to 17, 13 repeats, right? And you are not able to find out the number, the exciting integers in this case. So, what are you observing here? Whenever prime numbers, it happened with 11, it happened with 13, it happened with 17, right? Whenever the prime numbers occurred, there were no exciting subsets because repetition occurred here. 13, repetition again was there, 17, repetition again was there, right? So that means whenever prime numbers occur, we can find the exciting subset, right? Now he says from n varying from 10 to 89, how many exciting subsets would be there? Now we know n is equal to 11 will have 13, 17, and then next one would be 19, then 23. You just need to count how many prime numbers are there till 89, right? And that you obviously can. That is why the answer will turn out to be 20. On to the next one. Now he says again, consider a 6 into 6 array of equally spaced points. Now you need to count the rectangles which are not squares, right? Which is given to be m. You need to find the value of m plus 2 divided by 5. Basically, you need to find the rectangles. Mind it is given in the question that 1 into 2 rectangle is different from 2 into 1. So I need to count this as well as this, right? Okay, let's start. Now squares we have already exhausted. Now if I need to talk about rectangles, the first rectangle that I can think of, that is 2 into 1 type. Now 2 is length, so I will take length to be this side and width to be this side. Just a convention, right? So 2 into 1, so that means I am talking about this rectangle. 1, right? 2, 3, 4. 4. 4 here, 4 here, 4 here, 4 here, 4 here. So that means 5 into 4, right? Then, mind it, 2 into 1 can be exhausted with 1 into 2. In the similar way, I'll have, in that case, 5 into 4 again. So I will just multiply by 2. Right? So I will count this and I'll count this. Since this figure is symmetrical, it is 6 into 6 array. I do not need to worry about it. Right? So next is 2 into 2 is done. 2 into 2 cannot be 2 into 3. Right? That means 2 in this direction, 3 in this direction. So 1, then 2, then 3, then 4. 4 is done. Now, how many times? Let's see. This was 1, 2, 3. Yeah. Oh, I need to write it here. 3 into 4. Right? Now, obviously, I will include 3 into 2 also. That will be into 2. Done? Done. So, 2 into 3 is done. Next is 2 into 4. Right? 2 into 4, 2 this direction, 4 in this direction, 1, 2, 3, 4. So that means 1, then 2, then 3, then 4. 4 again, obviously 4 had to be there. And see, I'll have 1 here, 2 here. So 2 into 4. Again, along with this, I'll do 4 into 2. So that will be into 2. Done? Then I'll take 2 into 5. Right? 2 into 5. So 1, 2, 3, 4. 4, and obviously just 1 I am having, so I'll write it for the sake of it, 1 into 4. And again 5 into 2, if I need to count, that would be into 2. Done? So I've exhausted all those cases where 2 is the length, right? Let me talk about the cases when we have the length 3, right? So obviously 3 into 1, I need to talk about 3 into 1, and I need space also. Cool, we'll figure it out. 3. So 3 in this direction, 1 is this direction. 1, 2, 3. 3 and 5 there, so that means I'll get 5 into 3. Right? I also want to count 1 into 3 simultaneously, so into 2. Done? Now I will shift my rectangles this side. Cool. So 3 into 1 is done. 3 into 2 already counted, so I will not count it. 3 into 3, that will be a square. So next is 3 into 4. Cool. 3 into 4. Right. 3 and 4. 1, 2, 3, 4. Right. So 1, 2, 3. Right. And it will be 2 times. So 2 into 3. Right. I also want to count 4 into 3, and that will be into 2. 3 into 4 is done. Next is 3 into 3 into 5. Obviously 1, 2, 3, 4, and 1 there. So 1 into 4. Come on, 4. Let me see. My bad. 1, 2, 3. It has to be 3. From here I can see it. Right? Out. Also I want 5 into 3. That means into 2. 3 cases exhaust. Now 4, 1. 4 into 1. 4. 1, 2, 3, 4. So that means 1, 2. 5 times. So 5 into 2. Now I also want 1 into 4. So that is into 2. More space we need. Right. Then 4 into 2 is done. 4 into 3 is done. 4 into 4 is a square. Next is 4 into 5. Right. 4 into 5. So 1, 2, 3, 4. 1, 2. So that means I am getting 1 into 2. Right. I also want to count 5 into 4. So that means that will be into 2. Now last case is left. So I'll write it here. Because we are tight with space. Because I still need these. Don't worry. Now 5 into 4 is done. So 4 exhausted. Right. So then 5. 5 into 1. Let's do that. 5 into 1 is easy. 1, 2, 3, 4, 5. But I'll still write it how we are writing. So I'll say 5 into 1. I need to exhaust 1 into 5. So that means into 2. Right? Okay. Now 5 into 2 already done. 5 into 3 already done. 5 into 4 already done. 5 into 5 no need to be counted. Right? So I've exhausted all of these rectangles. Let me check whether I have missed any or not. So 2 into 1 is done. Okay, hopefully we haven't. Right? Now, moving on to the next one. Now, we have counted those rectangles whose sides were parallel, were something like this, or this. Vertically or horizontally. What if I have a diagonal rectangle? And in the sense, whose side is a diagonal of the square. Right? Now, we'll adopt the same method that we did in terms of squares. Right? Now, if I consider 2 into 2 square, do you think you will get any rectangle? The answer is, of course not. Right? Let me consider this one, 3 into 3. Now, you need to have rectangle, not a square, careful. Right? So, I can have rectangle. So, again, I'll start with this one. If I take this one, the rectangle. This is a square, so I will not take it. This is the rectangle that I can take. Right? Now, this rectangle, I've taken it from this side. I can take it from this side as well. Done? Right. Now, with this diagonal, I have the rectangle. Now, with this, I will not have any other. Now, if I take the diagonal one, already counted. So, just look at it. You think you can get any more rectangles? The answer is no. That means from each 3 into 3, you are getting 2 rectangles. We know that they are 3 square, 9 in number basically, and I am getting 3 from each of, I am getting 2 from each of these, so into 2. So, this I need to count. I am marking this one. Right? Obviously, 2 into 2, we didn't get any. 1 into 1, obviously, we will not get any rectangles. Done. So, 3 into 3 done. Let me talk about 4 into 4. That's this one. How many rectangles would be there? Let's see. Now, again, let's start with the diagonal one first. So, I will have this one. Mind it, I will not take, now it looks like, I will not take this one because this rectangle already has been counted here. So, I will not count it. Right? That means I will only take the rectangles where the vertices are at the ends of this. So, vertex is here. Vertex of the rectangle is here, here, here. Right? Any other rectangle. Obviously, I can have this rectangle as well. Now, any other rectangle that we can form? Obviously, we cannot have something like this because that would be a square. We cannot have something like that. Again, because that will not be the right way. We have that one. No, that would be a square again, so I can't. And if I take this and this, no, if I take this and this, no, again a square. So that means these are the two rectangles that I'm getting, right? That means from each 4 into 4 squares, I'm getting two rectangles. So into 2. Right. Now till now we have counted rectangles in 3 into 3 square, 4 into 4 square. Now this is the main one where we need to exhaust every rectangle. Now let's see. Now suppose I have I'll start like this again. This is one of my rectangles. The second rectangle. Right? This is the easy one. Cool. Yeah, it should pass through this. It's not exactly equally spaced, but we get the point. Right. Next one. Now parallel to this only I'll check for this. So maybe I can have something like this. Another rectangle, another rectangle. So in total, from this side also, I'll just draw it. Till now, I have 4 rectangles. So let me just write it. 4. Right. Now I have taken sides which were parallel, which were diagonally like this. Right. Now this is done. This is done. From here, I already counted. From here, already counted. So that means when side is in this slope, my cases are exhausted. Now let me change it. So keep this point fixed. I will talk about this slope now. Right. Whether I can find anything from this one or not. So let me change. Yeah. So this one. Right. Now this one will go up to this and up to this. Another rectangle, right, in this slope. Now parallel to this slope I'll check. So parallel here, I can look for that. Just the adjacent point and just the adjacent point. Right? Now 2 in this direction, 2 you can make it here. I'm not making it because otherwise too many rectangles would be there. You will stop seeing the rectangles only. So in total I got 4. Right? Okay. Now let's move on. Let's change our orientation again. So we were doing this orientation. This one we have completely exhausted. Now the question is, will you have an orientation which is like this? The answer is no. So we have exhausted all the slopes when we have taken this point. So let's change the point only. Now let me take this point. Right? First of all, obviously I will not take this slope. I will start with this slope itself. Right? Now I need to look for my rectangle. So it would be something like this. Right? Okay. Done? Now, parallel to this, if I can find it, my job would be done. It is something like this. Right? So, point here, point hopefully here, and got it. Right? Now, 2 I found in this one. Now, from 2 here, so in total, I will get 4. Right? Now, this is also done, parallel is also done. Now, I'll change. I will use the black one now. Right. Now, this slope is done. Now, the question is, do you think I will get a rectangle when I join this one? Right? The answer is obviously yes. But we have already counted this one, so I will not, because this slope already has been counted, so I will not count this one. So let me change. This is done. So let's start with this one now. If I can find out any rectangle in this direction, the answer is no. This is already done. 4 into 4, right? This because I'm not finding any rectangle. So this is also done. Now, obviously, I will not get any in this orientation, done. Right? Now, the question is, are there more rectangles or not? See, so I've exhausted this point. Now, I can move to this point. Mind it, I have, see, with this as a slope, I will not find any rectangle. Right? With this as the slope, no rectangle. With this as the slope, I have my rectangle. This as the slope, no rectangle. Done. So this, again, you can exhaust it. These ones you will not get. This one already counted. Further, you will not get it. So in total, I've exhausted all of these, and these are nothing but 12 in number. Right? So I got from which was only 1, 5 into 5 square, I got 12 more. So in total, how many? This plus this plus this plus this, this, and this one, and this one. If you add them up, they will turn out to be 208. Right? Yes. They will turn out to be 208. Right? Obviously, m is that you need to find m plus 2 divided by 5. It will turn out to be 42. The correct answer is 42. Right? For the next question, which is the C part, he says number of rectangles including squares. Squares you found out in the first question. They were what? 105, I think. 105. And rectangles you just found out, those are 208 in number. We need to find the total one. So add the 2, which will give you P. But you don't want P, you want P plus 15 divided by 4. And for the C part, that is why the answer is 82. So I'll repeat. For A part, we have the answer as 18. For B part, we have the answer as 42. And for C part, we have the answer as 82. Right? Now, with this, we are at the end of the discussion. I hope you learned something through this kind of video tutorial. Now, what you have to focus in your paper or while you're preparing, because you still have time, you need to focus on the techniques and the tools that you have. If you have a brand new question in front of you, what are the different things that you can think of? If something not working out, change the strategy. You will have plenty of time there, so that means plenty of techniques and tools to go through. Don't get stuck and be stuck at that problem. You have to get out of it. So that means you can use concepts from 6th class. You can use concepts for 9th class. So whatever tools you have, utilize all of them. Alright. So that's it, and I will see you.